This is Module 16, Section 10.5. In this section, we're going to look at rationalizing denominators. Remember from Section 10.3 that one of the rules for simplest radical form was that a radical was not allowed in the denominator of a fraction. This section discusses how to remove a denominator radical by a technique called rationalizing the denominator. To rationalize the denominator, simply multiply both the numerator and denominator of your fraction by a radical expression that will remove the radical sign in the denominator. In other words, using just basic fraction work, we're going to build the fraction up to get a denominator that will then give us a non-radical term in our denominator. So let's demonstrate this with some examples. Let's say I asked you to simplify and write in simplest radical form the square root of 1/5. Now you know from earlier sections that one of the rules of radicals is you can split that square root out to each of the numerator and denominator terms separately. And up in the numerator, that simplifies down nicely. The square root of 1 is 1. Square root of 5, though, is not a perfect square, so you can't simply put it in your calculator and simplify it. And there are no perfect squares in 5 that would allow us to write it in a simpler form. But the rule for simplest radical form is you're not allowed to have a radical sign in the denominator. So our technique is going to be to multiply or build up that fraction top and bottom so that the radical in the denominator cancels out. And so our method is going to be, we want to see if we can multiply that denominator by some radical expression that will give us something squared underneath the radical sign, and then the square root and the square will cancel themselves out and the radical sign will be gone. So you would agree with me that right now, underneath that radical, we have the square root of 5 raised to the first power. So if we multiplied that denominator by the square root of 5 to the first again, when we combine those two radical expressions into one radical expression, we'll have the square root of 5 to the first times 5 to the first, which is 5 squared, which of course is 25 if you just want to think about it in terms of memorization of perfect squares. Okay? And what that's going to allow us to do then is a square root and a square will cancel themselves out and we no longer need the sign, and we'll be able to pull out a 5 in the denominator. But you know from fraction work that if you're going to multiply the denominator by the square root of 5, you must multiply the numerator by the same thing or you've changed the fraction. Okay? So when we do that multiplication top and bottom, we get 1 times the square root of 5 in the numerator is simply the square root of 5. In our denominator, we've really done the work already. Square root of 5 times the square root of 5 is the square root of 5 squared, or the square root of 25 if you prefer. That allows us to pull out the 5, and that is our final answer in simplest radical form. Note that we cannot cancel the 5's because in the numerator, that's not really a 5, it's the square root of 5. So those do not cancel out, and that is our final answer. So let's look at this example. We've got 5 divided by the square root of 27 times a. All right, you cannot leave your final answer like that because there is a radical in the denominator. So we're going to split that radical sign out so that we've got the square root of 27 times the square root of a. Now at that point, let's see if there's anything we can do to simplify either of those. 27, if you break 27 down, 27 is not a perfect square, but notice that there is a perfect square in it. Right here, we have a factor that appears twice. 3 times 3 is 3 squared, or of course you might just recognize that 9 is a perfect square. So we can simplify the square root of 27, so let's do so. The square root of 27 is the same as the square root of 3 squared, or the square root of 9, times the square root of the 3 that is not part of that square. And that will simplify if we simplify the square root of 9 or the square root of 3 squared in our denominator to give us 3 square roots of 3. So we've simplified the denominator a little bit, but we still have that square root of 3, and we also have that square root of a that we were unable to do anything with. Notice that a is a to the first, and since the power is less than the index or the root, the square root of a is in simplest radical form. All right, so now if we look at that fraction, we've done everything we can in terms of just simplifying without rationalizing the denominator, but we do have to get those radical terms now out of the denominator. So in the case of the square root of 3 to the first, if we can make that 3 to the second power, then our power and our index will cancel themselves out and our sign will be gone. So to do that, we're going to multiply our denominator by the square root of 3 to the first, because 3 to the first times 3 to the first is 3 squared, or 9, and that is a perfect square. That'll take care of our square root of 3 factor. Of course, you have to multiply your numerator by the same thing, square root of 3 to the first. We also have to get rid of that square root of a factor. So we're also going to multiply by the square root of a to the first, because there's already an understood 1 there. 1 plus 1 is 2. That'll give us the square root of a squared, and that will get rid of the radical term in the denominator. But we have to multiply the numerator by the same thing. So now multiply that through and see what you've got. We've got 5 times the square root of 3 times the square root of a is equal to 5 times the square root of 3a if you recombine it into a single radical, which you want to do for your final answer. In our denominator, we've now got the 3 that we pulled out in our first step. We've got square root of 3 times square root of 3 is the square root of 3 squared, or the square root of 9. And we've got the square root of a to the first times the square root of a to the first, which is the square root of a squared. Because we managed to get our power and our indexes to match, we can cancel out those root signs in our denominator. That leaves us with, in our denominator, 3 times the 3 that we're pulling out times the a that we're pulling out. And so now we have 5 times the square root of 3a in our numerator, and our denominator is 3 times 3, which is 9. 9 times a is 9a. At this point, you want to see if there's anything maybe you could reduce. Notice you cannot reduce the a's because that's not really an a in the numerator, it's the square root of a. Ditto, you can't reduce a 3 factor out of your numerator and denominator because you don't have 3 in your numerator, you have square root of 3. Therefore, this is your final answer in simplest radical form. All right? Let's simplify the cubed root now of 3/5. First step, look underneath that sign and ask yourself, can I reduce or simplify 3/5 in any way before I apply any radical work? And the answer is no. So our next step is going to be, we're going to split out that radical sign to both your numerator and denominator individually. So we've got the cubed root of 3 divided by the cubed root of 5. Now neither 3 nor 5 is a perfect cube, and you can't break 3 or 5 down to get a perfect cube. Those are both prime. So our goal then to get our final simplified answer is we have to get the radical out of our denominator. So looking at our denominator as written, the cubed root of 5 is the same as the cubed root of 5 to the first power. There's an understood power of 1. If we can get that power to be a 3, our 3 power would match our 3 index and they would cancel themselves out. So in this case, what we're going to multiply by is the cubed root of not 5, but the cubed root of 5 squared, because then our power of 2 and our power of 1 will add to give us 5 cubed, and we will be able to rationalize our denominator. As always, what you multiply your denominator by, you must multiply your numerator by as well. And then do the math. Up in our numerator, we've got the cubed root of 3 times the cubed root of 5 squared. 5 squared, of course, is 25, so 25 times 3 would give us the cubed root of 75 up in our numerator. In our denominator, we've now got, if we leave it written as a power term, the cubed root of 5 cubed, 2 plus 1 is 3. If your power matches your index, your sign is gone. And now we've got the cubed root of 75 divided by 5. At that point, you'd want to ask yourself, is there anything more I can do with that problem? Although there is a common factor between 75 and 5, again, your numerator is not really 75. It's the cubed root of 75. So you cannot cancel out there, and that would be your final answer. All right, let's simplify. The cubed root of 2y squared divided by the cubed root of 9x squared. All right, up in our numerator, if we split those radicals out, we'd have the cubed root of 2, which cannot be simplified, and we've got the cubed root of y squared. That also can't be simplified. It's in simplest radical form because our power of 2 is less than our index of 3. In our denominator, if we split that out, we've got the cubed root of 9, okay, times the cubed root of x squared. Now the cubed root of 9, notice you could write as the cube root of 3 squared. But even if you write it as the cube root of 3 squared, your power is still less than your index. And so that cannot be simplified further as written. But we know that we can't leave our denominator like that. We have to rationalize our denominator. So starting with our cube root of 3 squared, if we multiplied that by the cubed root of another 3, which is 3 to the first, our 2 and our 1 will give us 3 cubed, and then we'll be able to cancel out that radical sign in the denominator. So that'll take care of our cube root of 9. Our cube root of x squared, we need another x, so there's 3 of them. So we're going to multiply also by a cube root of x to the first, which will take care of our cube root of x squared term. Numerator has to multiply by the same thing. So we've got the cube root of 3 times the cube root of x in our numerator. So now up in our numerator, if we combine all 4 of those radicals into one expression, we've got the cube root of 2 times 3 is 6, and then we've got x to the first and y squared in our numerator, none of which can be simplified. In our denominator, we've got now the cube root of 3 cubed, or the cube root of 27, times the cube root of x cubed. For both of those factors, we can then remove our radicals, and we now have the cube root of 6xy squared divided by what we pulled out here, which is just our bases, 3x. And that is our simplest radical form for that particular problem. All right, let's look at 1 divided by the square root of 32x. Square root has an understood index or root of 2, so I'm going to put that in and split it out. We've got 1 divided by the square root of 32 times the square root of x. Now if you look at 32 and break it down, we'll do that over here. 32, if you take a 2 out, leaves you with 16. Then 16, of course, will break down again. 16 divided by 2 is 8. 8, if you take out a 2, leaves you with 4. And then 4, of course, is 2 times 2. So 32 is 2 to the 5th. In this case, we want something that's a multiple of 2, though. 2 will not go into 5, but 2 would go into 4. So what we're going to do here in our denominator is we are going to write 32 as 2 to the 4th times 2 to the 1st. Notice 4 plus 1 is 5. That's a total of 5 factors of 2 that make up 32. And then, of course, the square root of x to the 1st, that is simplest radical form. You can't break that down. So we'll leave that as square root of x to the 1st for now. Now let's simplify what we've got. 2 goes into 4 and leaves you with 2. And because we canceled out our index, our sign is gone. In our denominator, 2 squared times the square root of 2 to the 1st times the square root of x to the 1st. Now to get rid of those remaining radicals in the denominator, we're going to have to multiply by the square root of another 2 to the 1st, which will give us 2 squared when we combine, and also a square root of x to the 1st, which will combine to give us the square root of x squared, which will rationalize our denominator. As always, you need to multiply your numerator by the same. So we're going to multiply top and bottom here by the square root of 2 to the 1st and the square root of x to the 1st. Now combine where appropriate. Here, 2 squared gives us 4. If we combine here, we've got the square root of 2 times the square root of 2 is the square root of 2 squared. And if we combine our x radicals here, we've got the square root of x squared. Power and index match and our sign goes in both of these cases. And our denominator then, bringing it over here, would be 4 times 2 times x, which is 8x in our denominator. Numerator, we've got 1 times the square root of 2 times the square root of x, simply gives us the square root of 2x in our numerator. And that would be our final simplified answer. All right, so let's look at this problem. We're going to simplify the 5th root of 32 divided by m to the 6th m to the 13th. All right, let's split out that sign. So that would give us the square root of 32 divided by the square root of m to the 6th times the square root of n to the 13th. Oh, I made a mistake there. That's not square root, that's a 5th root. So we'll change that right here. We're looking at the 5th root, not the square root, on this particular problem. Okay, now notice that on the right-hand side of the screen, we already broke 32 down, and we found that 32 does have a perfect 5th power. In fact, 32 is a perfect 5th power. 32 is 2 to the 5th, and so we are taking the 5th root of that, and if our power and our index match, they go and leave us just with a 2 in our numerator. In our denominator, though, notice that for both the base m and base n, our power is larger than our index. So we know we can simplify it. So we're going to use the trick we talked about in earlier sections and ask ourselves, will 5 divide evenly into 6? And the answer is no, it does not. So start decreasing that power by 1 and ask yourself the same question. If 5 won't go into 6, will 5 go into 5? And the answer is yes, it will. So we're going to rewrite m to the 6th as m to the 5th times m to the 1st. 5 plus 1 is still 6, okay? And we're taking the 5th root of both of those. Do the same thing with your n. 5 will not go into 13. 5 will not go into 12. 5 will not go into 11. but 5 will go into 10, so we're going to rewrite that as the 5th root of n to the 10th times the 5th root of however many more n's you need to get to 13, and that would be n cubed. All right, so we're going to simplify where we can. So here our 5's cancel, and we'll be able to pull out an m. Here, 5 goes into 10 and leaves us with 2, and we'll be able to pull out an n squared. So now we've got m times the 5th root of m times n squared times the 5th root of n cubed. Now that helped us some, but we are going to have to rationalize the remaining radicals. So we're going to need to multiply by the 5th root of m to the 4th, because we need 4 more m's in order to get rid of this radical. And we're also going to have to multiply by the 5th root of n squared, because we need 2 more n's to get up to a total of 5. Okay, numerator, you have to multiply by the same thing. So we've got the 5th root of m to the 4th times the 5th root of n squared. And now we've got 2 times the 5th root of m to the 4th times the 5th root of n squared is equal to 2 times the 5th root of m to the 4th n squared in our numerator. And in our denominator, we've got here the 5th root of m times the 5th root of m to the 4th will give us the 5th root of m to the 5th, which will allow us to pull out another m. We had an m already, so m times m is m squared. And then here we had n squared. We'll be able to pull out another n here, because the 5th root of n to the 5th is n. N squared times another n is a total of n cubed in our denominator. And that would be our final answer for that problem. But what about a denominator that is not a single term? How do you rationalize those? Well, you need to multiply the numerator and denominator of the fraction by what's called the conjugate of the denominator. So conjugate, using a very simple definition, is simply the same terms in the same order, but opposite operation between the two. So for example, if you had a plus b in your denominator and you wanted to find the conjugate is the same terms, a and b, in the same order, but we take the opposite operation. So if it's addition, it becomes subtraction. Ditto, if your denominator was the square root of 2 minus 3, the conjugate is the square root of 2 plus 3. Note that this will remove all radicals from the denominator, but not necessarily the numerator. However, remember, radicals in the numerator are fine. It's only radicals in the denominator that we're concerned with. So let's look at this problem. 6 divided by 2 minus the square root of 7. The way you're going to recognize this problem is there is subtraction or addition in the denominator, and that indicates to rationalize that denominator, if there's a radical term in the denominator, which there is, you're going to multiply by the conjugate of the denominator. Make sure that you put parentheses around that denominator group, because you are going to multiply by a group as well, and that will emphasize to you that this really is a FOIL problem in your denominator. So multiply by the conjugate of the denominator, and as always, what you do to the bottom, you have to do to the top as well. Now, up in your numerator, that's a distributive property step. So 6 times 2 is 12, plus 6 times square root of 7 is exactly that, 6 times the square root of 7. In our denominator, we've got a binomial times a binomial, so that's a FOIL problem. But it also is a special type of FOIL problem. If you think back to your algebra, earlier algebra days, there was a special products that said if you ever take a binomial, say x plus y, and multiply it times a binomial x minus y, okay, where it's the exact same binomial, but the operation is opposite. In other words, you're multiplying conjugates. If you FOILed that out, you'd get x squared minus xy plus xy minus y squared. And your outer and inner product canceled out, leaving you with simply the first two terms multiplied together minus the last two terms multiplied together. That's the difference of two squares in reverse. Okay? So when you're rationalizing denominators, that's always true in these problems as well, because you're always multiplying by the exact same binomial, except that the difference is they're opposite in sign. So if you simply take the first two terms, which in this case is 2, okay, and square it, and subtract from that the product of the last two terms, which would be, of course, the square root of 7 squared, that will be your simplified denominator. If you're not sure about that and you always want to FOIL that denominator out, you can certainly do that too. This is just a little bit of a shortcut for you. So now we've got 12 plus 6 times the square root of 7 over 4 minus the power cancels out the square root. Okay, power and index match, the sign goes. So we've got 4 minus 7 in our denominator. 4 minus 7 is negative 3. So we've got 12 plus 6 square root of 7 over negative 3. Now at this point, we could factor out of our numerator a positive 6, which would leave us with 2 plus the square root of 7 over negative 3. And because we have our numerator factored, we can simplify by dividing negative 3 out of top and bottom. If we take a negative 3 out, 6 divided by negative 3 is negative 2. And our denominator is a 1, and anything divided by 1 is itself. And so our final answer here would be negative 2 times the quantity 2 plus square root of 7. Let's look at this problem. Negative 8 divided by the square root of y plus 4. First step, notice that the denominator does have addition in it and there's a radical in the denominator. So to rationalize that denominator, we're going to need to multiply by the conjugate of that denominator, top and bottom. Up in the numerator, that's a distributive property step. So negative 8 times the square root of y is exactly that, negative 8 square roots of y. And negative 8 times negative 4 is plus 32. In our denominator, you can either FOIL that out, or you can remember that it's always the first term squared minus the last term squared in the simplified form. So we'll use that little shortcut step. We've got the square root of y squared minus 4 squared. In our denominator, the square and the square root will cancel themselves out, and we can pull out that y. So now we have negative 8 square roots of y plus 32 over, in our denominator, y minus 16. Now at that point, there's really nothing further we need to do unless there's a common factor we could factor out. In this case, though, there is not, although you can take an 8 out of your numerator. By doing so, that doesn't allow you to simplify in your denominator, and so we'll just leave it in that form. Okay, let's look at this problem. Square root of 2 minus the square root of 3 divided by the square root of 2 plus the square root of 3. Again, there's addition in the denominator, so we're going to have to multiply by the conjugate to rationalize that denominator. So use the same terms and change the sign. Up in the numerator, because there's more than a single term up here as well, You want to put parentheses up there as well, because you now have a FOIL problem in your numerator as well. Now in our denominator, we can use that shortcut step because this is a denominator multiplied by its conjugate. So we can take that first term and square it and subtract off that second term squared, which is going to give us, after our power and our index cancel out our radical sign, we've got 2 minus 3 in our denominator. Now in our numerator, though, notice that these are not conjugates. Okay? Therefore, we will have to FOIL that completely out. So square root of 2 times square root of 2 is square root of 2 squared. Our outer product will be square root of 2 minus square root of 3, which is minus square roots of 6. Inner product is the same. Minus square root of 3 times minus square root of 2, again, is minus square root of 6. And last two, negative square root of 3 times negative square root of 3 is positive square root of 3 squared. So simplify our numerator. Here our power and our index match in our first and last term. So now we've got 2. Notice we have some like terms. Minus square root of 6 and minus square root of 6 is minus 2 square roots of 6. And then we've got plus 3 on the end. Denominator, 2 minus 3, of course, is negative 1. Combine like terms in our numerator. 2 plus 3 is 5, minus 2 square roots of 6 divided by negative 1. To get rid of that denominator, I'm going to move that negative 1 up in the numerator. Now there's different ways you can think about that. If you think about multiplying top and bottom by negative 1, that'll give us a positive 1 in our denominator, and anything divided by positive 1 is simply itself. So really, we only need to do the work in our numerator. And so we get negative 5 plus 2 square roots of 6 as our final simplified answer. And this brings us to the end of Module 16, Section 10.5 material. You should now complete the homework for Section 10.5 found in my math lab. And when you have successfully completed that homework, review all the material for Module 16 and complete the Module 16 exam found in my math lab. After successfully completing the Module 16 exam, you may proceed to the Module 17 videos.